April 17th, 2025, 9 a.m. Eastern Time. A live broadcast begins at the University of Cambridge, and within minutes, newsrooms across the planet stop everything else they are doing. Astronomer Niku Madhusudan and his team announce that the James Webb Space Telescope has detected, for a second time, a chemical fingerprint inside the atmosphere of a planet called K2-18b, a fingerprint that, on Earth, is produced by nothing except living organisms. The molecule is dimethyl sulfide, and its cousin dimethyl disulfide, gases that, on our world, come almost exclusively from marine phytoplankton and bacteria drifting in the ocean. Within hours, the story is everywhere, and for a brief, dizzying moment, it feels like humanity is standing at the edge of the single greatest discovery in the history of science. K2-18b sits 124 light-years away, orbiting a small, cool star, and its atmosphere appears to hold these biosignature gases at concentrations reported to be up to 1,000 times higher than anything found on Earth. If that number holds, it does not just suggest simple microbial life. It suggests an entire hidden biosphere, teeming and thick, buried under clouds we cannot see through, on a world no human will ever set foot on. But then, just months later, the panic of excitement gives way to a colder, more uncomfortable kind of panic. A follow-up analysis from NASA researchers, released in July of 2025, walks the confidence level back from 3 sigma down to roughly 2.7 sigma, far below the 5 sigma gold standard that science demands before anyone can call a result a genuine discovery. Other teams argue the signal could be explained by mundane, non-biological chemistry, like ethane, hiding inside the same noisy data. So which is it? Are we looking at the chemical breath of an alien ocean, or an illusion built from statistical noise, 124 light-years from home? Nobody knows yet, and that uncertainty is exactly why this moment matters so much. Because if the universe truly is on the verge of handing us proof that we are not alone, then the next question is not whether alien life exists, but what in the universe could that life actually look like? Right now, NASA is not waiting for the argument over K2-18b to be settled. It is already building the next tool for the job, a mission called the Habitable Worlds Observatory, a next-generation space telescope designed with one goal in mind: to find at least 25 potentially habitable exoplanets and study each one directly for signs of life. Its launch is not expected until sometime in the early 2040s, which means an entire generation will grow up wondering whether we are alone before that telescope ever opens its eye toward the stars. But we do not have to wait 2 decades to start imagining what it might find. Astrobiologists have already been building detailed science-based models of what alien organisms could look like under wildly different planetary conditions, using nothing but chemistry, physics, and the hard lessons of evolution here on Earth. So let's take that journey now, planet by planet, and meet the creatures that might be waiting out there. On Earth, life needed water to begin. About 4 billion years ago, in the shallow, chemical-rich oceans of a young planet, the first simple cells appeared, and everything alive today descends from them. So it makes sense to start our search with a true water world. That world is TOI 1452b, an exoplanet just 100 light-years from Earth, roughly 1.5 times Earth's diameter and nearly 5 times its mass. What makes it extraordinary is not its size, but its composition. Scientists estimate that as much as 30% of this planet's entire mass could be liquid water, which works out to roughly 7,000 times more water than exists across every ocean, lake, and ice cap on our own planet. This is not a planet with oceans. This is a planet that is an ocean, with no continents to interrupt it. To imagine what might swim in it, scientists lean on a concept called convergent evolution, the idea that unrelated species, facing the same environmental pressures, tend to evolve strikingly similar solutions. Dolphins, ancient marine reptiles, and fish all evolved from completely different ancestors. Yet all 3 independently developed the same sleek, torpedo-shaped bodies because water rewards that shape with speed and efficiency. It stands to reason that fast-swimming predators on TOI 1452b would look eerily similar. But size is where things get strange. Gravity on this world is only slightly stronger than Earth's, and in water, gravity's pull barely matters, because the water itself supports the weight of anything living in it. That means evolution here faces almost no upper size limit. Creatures 200 to 300 feet long are plausible, 2 to 3 times the length of a blue whale, which would suddenly become an unremarkable mid-sized animal in this ocean rather than the largest creature ever to exist. Picture something with a massive sail-like fin running down its spine, not for balance, but functioning as a biological antenna, capable of firing off pulses of light in patterns other members of its species can read, an entire language built from bioluminescence instead of sound. And because a body that size needs staggering amounts of energy just to stay alive, Its skin might function almost like a solar panel, absorbing starlight filtering down through the water and converting it directly into a kind of bioelectricity that powers its muscles and nerves, reducing how often it needs to hunt at all. The deeper you go into this ocean, the stranger and darker things become. On Earth, even at the crushing depths of the Mariana Trench, 11 kilometers down, life still exists. Tiny amphipods and sea cucumbers surviving under roughly 1,100 atmospheres of pressure. But toy 42B's ocean holds 7,000 times more water than Earth's, and its depths may plunge far beyond anything we have on our own planet, with pressures at the bottom potentially exceeding 8,000 atmospheres. At that pressure, a steel submersible built with our best modern engineering would be crushed into a sheet of metal in an instant. Any organism surviving down there could not rely on rigid structures like bones or shells, because rigid structures shatter under that kind of force. Instead, biology would likely favor soft, gelatinous, almost liquid-filled bodies built to flex and absorb pressure rather than resist it. Eyes would be useless in absolute darkness, so evolution would likely replace them with hypersensitive organs built to detect vibration, chemical trails, or even electromagnetic signals, essentially reading the water itself instead of seeing through it. Some of these creatures might still glow, using bioluminescence the way Earth's anglerfish do, dangling a lure of light to draw in curious prey before striking from total darkness. It is a world of endless ocean and quite possibly endless biological invention, but it is far from the strangest place life could take root. What if life did not need an ocean or solid ground at all? In 1976, astronomer Carl Sagan, working with astrophysicist Edwin Salpeter, proposed something that sounded more like science fiction than science, that life could theoretically exist floating permanently in the clouds of a gas giant, never once touching a surface, possibly not even aware that a surface exists. To explore that idea, we travel to Co-Rho-T 9b, a gas giant 1,347 light-years from Earth, close in size to Jupiter but slightly lighter. Deep inside a gas giant, conditions are lethal: hurricane winds, extreme pressure, and radiation. But high in the upper atmosphere, conditions moderate dramatically. And in Co-Rho-T 9b's case, cloud layer temperatures range from about -25 to positive 150 degrees Celsius, a range wide enough for complex chemistry and potentially complex biology to function. Sagan and Salpeter theorized that on a gas giant old enough, with an atmosphere rich in organic molecules, life could have had billions of years to develop into fully airborne organisms. Picture creatures shaped like enormous balloons or airships, their bodies built from an extremely thin membrane inflated with lighter-than-air gas, keeping them suspended at exactly the altitude where temperature and pressure are survivable. That membrane would likely serve double duty, partially absorbing starlight as an energy source, a strange, exotic cousin of photosynthesis running on entirely different chemistry than anything on Earth. To survive constant ultraviolet bombardment with no ozone layer to protect them, these creatures might glow in shades of red, blue, or green across their entire surface, using specialized pigments that absorb dangerous UV radiation and re-emit it as harmless visible light, not unlike coral reefs here on Earth. Beneath that glowing membrane would sit a dense organic core, housing sensory organs, something like a nervous system, and the biological machinery for feeding on nutrients drifting through the clouds. Sagan himself speculated the largest of these creatures could reach roughly a mile across, but there's nothing stopping an even more extreme version of this idea, a creature the size of Mount Everest, drifting silently through alien clouds, its internal organ core alone rivaling the Empire State Building in scale. It sounds absurd, almost like myth, and yet Sagan never claimed this life definitely existed. He simply insisted that the boundaries of what is biologically possible in the universe are far wider than human imagination tends to assume. Extreme environments do not rule life out, they just make it stranger. Which raises the question, what happens when the extreme factor is not temperature or radiation, but the sheer, bone-crushing pull of gravity itself? That brings us to LHS 1140b, located 49 light-years away, about 1.5 times Earth's size and nearly 6 times its mass, with gravity roughly double what we experience here. Under that kind of relentless pressure, evolution stops rewarding risk and starts rewarding raw endurance. There is little room for fragile, graceful body plans. Instead, picture squat, powerful creatures with thick, column-like limbs built purely to support their own crushing body weight, moving slowly and deliberately because speed simply is not survivable here. Flight would be almost impossible, since the gravitational pull required to lift off is simply too strong. Even jumping would be rare. Life here would be built low and heavy, crawling or using multiple sturdy limbs like the legs of a machine straining against constant resistance. At an average temperature of around -43 degrees Celsius, comparable to Earth's polar regions, these creatures might also need thick, layered natural armor to survive the cold, something resembling chitin but tougher and more flexible, built to insulate as much as protect. In periods of extreme cold, their metabolism might slow to nearly nothing, breathing and heartbeat dropping to barely perceptible levels, a kind of suspended animation not unlike Earth's sloths, animals that already move at only about 5 feet per minute. If a human somehow visited a world like this, in full gravity gear, they would move through it like a superhero, impossibly fast among creatures that barely seem alive at all. Now flip that equation. What happens on a planet where gravity is weaker than Earth's, not stronger? This is where things get genuinely terrifying. TRAPPIST-1d, 41 light-years away, is about 30% smaller than Earth and 60% lighter, giving it roughly half of Earth's gravitational pull. Weak gravity does not calm evolution down. It removes the ceiling on how large and dangerous a predator can become. On Earth, roughly 110 million years ago, a herbivorous dinosaur called Sauroposeidon stood about 60 feet tall and stretched 100 feet long, weighing around 132,000 pounds, tall enough to peer directly into a 6th-story window. And it needed about 440 pounds of vegetation every single day just to survive. Now imagine that same evolutionary arms race playing out for billions of years on a planet with half Earth's gravity, where growing larger costs far less energy. Herbivores could plausibly reach heights of 160 feet, structures the size of a 16-story building, weighing up to 440,000 pounds. As competition for food intensified among giants that size, some would inevitably turn predator, hunting the others simply because there was not enough vegetation to sustain them all. Picture a mouth the size of a city bus, teeth as long as a grown adult is tall, and not just one of these predators, but thousands. An entire ecosystem where hunger, not strength, decides who survives each day. Trees on a world like this could stretch 500 to 650 feet into the sky, matching 60 or 70-story buildings. And with gravity making flight far easier, the skies could hold airborne creatures the size of a Boeing 777, gliding silently above a landscape more brutal and untamed than Earth's Jurassic period ever was. Every creature we have imagined so far, and every living thing on Earth, including us, is built around one single element: carbon. Carbon forms strong, flexible, endlessly variable chemical bonds, including bonds with itself, which is exactly why it works as the building block for DNA, proteins, fats, and every other molecule life depends on. But some scientists believe life elsewhere in the universe might not need carbon at all. Researchers at the University of Wisconsin-Madison combed through hundreds of scientific papers and cataloged roughly 270 chemical reactions capable of autocatalysis, meaning a reaction that helps trigger its own repetition, a key ingredient for anything resembling growth or evolution. And many of these reactions did not involve carbon at all. Some centered on silicon instead, carbon's chemical cousin, an element also capable of forming long, complex molecular chains. That brings us to Kepler-62f, 1,200 light-years away, about 40% larger than Earth, with a plausible atmosphere and even oceans. Under the high heat and pressure this world may experience, silicon-based life becomes a real theoretical possibility. Organisms built not from flesh and blood, but from durable silicate compounds, with smooth or angular crystalline shells, strange multi-limbed forms, or bodies with no fixed shape at all. Some might be massive and nearly stationary, resembling boulders more than animals, while others slide or roll slowly across the surface. Their biology would run almost entirely differently from ours. Chemical reactions involving metals instead of breathing oxygen, slow mineral absorption from rock and soil instead of eating, and reproduction that looks more like crystal growth splitting apart under heat or radiation than anything we would call birth. These beings might move so slowly that a human observer would never even register them as alive, mistaking them for strange rock formations rather than living organisms. Without DNA, scientists speculate that heredity here might be carried by an internal crystalline matrix, information encoded not in molecules, but in the geometry, density, and electrical charge patterns of the structure itself, with mutations arising from irregularities in growth caused by heat, pressure, or chemical impurities, and natural selection quietly favoring whichever structures proved the most stable and durable over time. Science fiction has actually explored this idea before real astrobiologists ever formalized it. In the original Star Trek series, a creature called the Horta was depicted as a silicon-based life form burrowing through solid rock and dissolving stone with acid rather than digesting organic food. And for decades, that was treated as pure fantasy. But if the University of Wisconsin research holds up, something like it may not be so far-fetched after all. A more mobile, more aggressive branch of silicon-based life could plausibly stand roughly human height, somewhere between an insect and a living crystalline statue with sharp, semi-translucent armor plating instead of skin. It would not breathe the way we do, would not eat the way we do, and might not even move on a time scale we could perceive without watching for hours, yet by every meaningful biological definition, it would still be alive, just built from an entirely different chemical alphabet than the one written into our own DNA. We still have not found a single confirmed piece of alien life, not even a microbe. And the more scientists study the universe, the more they suspect that the forms life could take stretch far beyond anything the human imagination has produced on its own. But there is a deeper, stranger question waiting behind all of this. What if some alien life did not just survive its planet, but eventually outgrew it entirely? What if right now, somewhere out there, a civilization exists that has learned to harness not just a planet's resources, but an entire star or an entire galaxy? In 1964, Soviet astronomer Nikolai Kardashev proposed a framework for measuring exactly that kind of advancement, now known as the Kardashev scale, and it gives us a genuine roadmap for imagining just how far a civilization could climb. Many scientists now classify humanity as type 0 on this scale, a civilization still bound entirely to its home planet, dependent on finite resources, only just beginning to tap wind, solar, and nuclear power, and still deeply vulnerable to climate change, resource depletion, and planetary disaster. Our reach barely extends past our own moon. Yet the leap from type 0 to type 1 is considered the single most critical transition a civilization can make, requiring humanity to set aside tribal conflict, unify as a single species, and learn to manage the entire planet as one connected, sustainable system. A true Type 1 civilization would have achieved full mastery over its homeworld, controlling essentially all of the energy available on the planet's surface. Imagine controlling weather itself, steering hurricanes away from population centers and redirecting rainfall toward drought-stricken regions. Picture deserts covered edge to edge in solar arrays, entire mountain ranges lined with wind turbines, and a global grid of fusion reactors delivering clean, essentially limitless power to every city on Earth. A civilization at this level could reshape coastlines, build entirely new landmasses, and begin the earliest stages of terraforming other worlds within its own solar system. Artificial intelligence would be seamlessly woven into daily life. Nanotechnology would transform manufacturing and medicine, and the first real steps toward interplanetary colonization would already be underway. But a Type 1 civilization is still, fundamentally, a prisoner of its own solar system no matter how advanced its technology becomes. A Type 2 civilization breaks that barrier entirely, harnessing the total energy output of its own star, and this is exactly where a real Dyson sphere enters the picture. A fully solid shell around a star is considered physically implausible, but a Dyson swarm, a dense cloud of orbiting satellites or collectors surrounding the star, could accomplish the same goal. With that kind of energy at their disposal, a Type 2 civilization could theoretically move entire planets, construct artificial habitats large enough to house trillions of inhabitants, and possibly conquer aging and disease altogether, transferring consciousness into artificial bodies or even pure energy states. Interstellar travel becomes genuinely achievable, whether through generation ships or advanced propulsion systems, letting a civilization begin slowly seeding colonies into nearby star systems. Yet even here, a Type 2 civilization would likely remain confined to its own local stellar neighborhood. The vast gulf between stars, still an obstacle even to beings who can command the power of an entire sun. A Type 3 civilization abandons a single star system altogether, and instead commands the resources of an entire galaxy, potentially colonizing and utilizing millions or even billions of individual star systems. At this level, distance, as we understand it, starts to lose meaning, whether through some form of faster-than-light travel or exotic shortcuts like wormholes. A civilization this advanced might tap directly into the energy of a supermassive black hole sitting at its galaxy's core, physically relocate stars for massive engineering projects, or construct artificial megastructures on a scale rivaling entire solar systems. Some theorists go further still, suggesting such a civilization might have abandoned biological bodies entirely, existing instead as pure energy, vast distributed artificial intelligence, or forms of consciousness we simply have no framework to imagine. Kardashev's original scale stopped at Type 3, but later theorists pushed the concept even further, proposing a Type 4 civilization commanding entire galactic clusters and manipulating dark matter and dark energy as casually as we manipulate electricity, and even a hypothetical Type 5, mastering multiple universes entirely, a level of power that would be functionally indistinguishable from godhood. So here is the real question. If civilizations this advanced are even mathematically possible, why haven't we found a single trace of one? This puzzle has a name, the Fermi paradox, and it essentially argues that given the sheer age and size of the universe, life, especially intelligent life, should already be common and detectable, and yet, after decades of searching, we have found nothing. Part of the problem may be technical. Most of our search for extraterrestrial intelligence has relied on picking up radio and television signals, but those signals interact with charged particles in space and degrade badly over interstellar distances. And crucially, they are exactly the kind of signal only a Type 0 civilization, like us, would still be broadcasting. A Type 2 or Type 3 civilization might be transmitting on frequencies or through methods our current instruments are not even built to detect. Researchers have started approaching the problem differently, hunting instead for the unmistakable energy signature a Dyson swarm should theoretically produce, an unusual excess of infrared radiation, since any megastructure absorbing a star's visible light would inevitably re-radiate that captured energy as heat. A research initiative called Project Hephaestus did exactly this, sifting through photometric data from millions of stars, and after extensive filtering, isolated 7 candidate stars in the Milky Way, emitting infrared radiation that current astrophysics cannot fully explain. The next step involves detailed optical spectroscopy on each candidate to determine whether we are looking at genuine megastructures or something far more mundane like unusual dust or debris. For now, nobody can say for certain, but the search continues. There have already been a few tantalizing false alarms along the way. In 2016, the SETI Institute picked up a strong, unexplained signal from the direction of star HD 1645995, 92 light-years away. And for a moment, astrophysicists genuinely wondered if they had detected an advanced Type 2 beacon. It turned out to be nothing more exotic than a military satellite quietly orbiting Earth. In 2008, astronomers spotted what appeared to be a planet orbiting the bright star Fomalhaut, and by 2014 it had mysteriously vanished from view entirely. Some speculated its orbit had destabilized. Others wondered whether it had somehow migrated to orbit a different star altogether. Eventually, researchers determined the object was never a planet at all, but an enormous cloud of frozen debris, likely the aftermath of a violent collision between 2 icy bodies, an extraordinarily rare event to witness. If you enjoy speculation, it is at least fun to imagine a Type 2 civilization simply harvesting raw material for its next megaproject. Scientists have also turned their attention to enormous, mysterious, empty regions of space called cosmic voids, wondering whether a Type 3 civilization could theoretically be responsible for consuming or concealing the light of entire galaxies within them, though this idea remains firmly speculative and largely unsupported by current evidence. Maybe the reason we have not found anyone is simpler and stranger than any of this. Maybe we are just early. According to at least one computer simulation, conditions for intelligent life may actually have been more favorable roughly 4 billion years ago than at any point since, which raises an unsettling possibility that we might be one of the first civilizations to ever emerge, rather than a late arrival to a galaxy already full of neighbors. Or maybe, as physicist Neil deGrasse Tyson once joked, there are practical upper limits on how vast an organism or civilization can realistically become, since even information traveling at the speed of light would take unbearably long to coordinate a body or an empire the size of a solar system. Whatever the answer turns out to be, one thing is already clear. The line between what counts as biologically alive and what counts as a civilization is thinner than we usually assume, and somewhere between a glowing ocean giant the size of a city and a species that has learned to dismantle stars for spare parts, the universe may already be far stranger and far more populated than human beings have ever dared to imagine. Whether that turns out to be true will depend on missions still decades away, on telescopes not yet built, and on data we do not have yet. But for the first time in history, we finally have the tools to start asking the question seriously, and that alone should be enough to keep you looking up.